this is going to be one single field inflation in one lecture. So for those who knows what inflation is, what single field inflation is, it's going to be boring and non-informative. So let me pause for 20 seconds. Everybody is allowed to leave. Yeah, I'm serious. I mean, if you know what inflation is, there will be nothing new for you. What? So anyway, so what's inflation about? We have decided that we need some period of time at which the perturbations in the universe have been created, and this period of time should be long enough so that the entire visible universe is now in the causally connected region, within one causally connected region. So that's impossible at the hot epoch or radiation domination epoch. But inflation is precisely the mechanism that produces for you the long epoch, long in the sense that the entire visible universe becomes causally connected, and there is enough possibility to generate perturbations. Although historically it wasn't the main motivation, but essentially this is the upshot of inflation. What's the strength of inflation is that it is capable of creating the primordial perturbations, putting them behind the horizon, making them super horizon, etc. So what inflation is? Inflation is the epoch at which the scale factor goes like almost exponentially. H dt, that's by definition, but the point is that h is nearly a constant. Then what's important about the perturbations is that the behavior of physical momentum, p as function of time, is this of a mode, whereas the physical momentum decreases as usual. It redshifts exponentially in this case, whereas the hyperparameter stays constant. So early at inflationary stage, this momentum was much greater than h, and later on it becomes much smaller. So this is early times, and at late times the opposite happens. So these perturbations are sub-horizon early at inflationary epoch, and they become super-horizon later at inflationary epoch. Okay, that's the opposite compared to what we have at radiation domination or matter domination stage. So the inflation is precisely makes these things happen in correct way. So the first issue is it's important to understand when our visible universe actually exits the horizon at inflationary epoch, right? So we have some scale and time at which the perturbations comparable in size to our visible universe become super horizon, and megaparsec perturbations become super horizon, etc. So the question is, when does it happen? At what scales does it? At what value of the scale factor this happens? And this can be characterized by the number of e-foldings between this moment of time when our visible universe exits the horizon and the end of inflation. This is called e to the NE, where NE is the number of e-foldings between these two epochs. Okay, so it should be useful to understand what this number of e-foldings is, and what we know is that the crossing time, k over crossing time, crossing scale factor at crossing time, is of order of the inflationary Hubble parameter, and at the same time this momentum today is of order of the present value of the Hubble parameter, if we are talking about cosmological scales today, which means that the ratio between the crossing time and crossing scale factor crossing and today is of order of h naught over h at inflationary epoch. Okay, and then you can estimate what this ratio is by saying that this ratio is just a to end of inflation times the a at end of inflation and today. This is e to the number of e-foldings. That's an important number. And this is the redshift or inverse redshift by the end of inflation. It characterizes how much the universe expanded from inflationary epoch until today. And there is quite considerable uncertainty in here, and that's because we don't quite know how inflation ends, what happens after inflation, how does the universe get reheated after inflation. Therefore, there is quite a bit of uncertainty here. The simplest assumption you can make is that the reheating is instantaneous. So our sequence of events in general is that we have inflation, then we have reheating epoch, at which some mechanism transforms the energy of inflaton into heat, and then we have radiation domination and matter domination, etc. And there is some uncertainty in here. If we assume that this period is very short, then things are simpler. I can write down this ratio roughly within factor of order 100 as a ratio of temperatures today and at reheating. This is not precise, but for our purposes it's okay. And also I can write that the temperature at reheating squared over m Planck, again within a factor of maybe 100 or 10, is equal to the Hubble parameter at reheating. If it's instantaneous, then it's the same thing as the Hubble parameter at the end of inflation. Okay, so all in all, we get that the e to the n e-foldings is, in this case, is of order of T naught over H naught, which come from, so I require, sorry, I make this requirement. This is e to the number of e-foldings, and this ratio I estimate this fashion. So here is temperature over the Hubble parameter times square root of inflationary Hubble parameter to the present to 2m Planck. Okay, that comes from the reheating temperature. So, and in fact there is another unknown coefficient which can be large, but not huge or small, depending on the, actually small, depending on the dynamics and length, essentially, time duration of the reheating period. Now, the number of e-folding is logarithm logarithm of this thing is 67. Logarithm of this thing is unknown. We don't know exactly what the Hubble parameter at inflation is, but if we think that the Hubble parameter at inflation, which is often the case over M Planck, is on the level 10 to minus 6 to 10 to minus 10, then in logarithmic scale you make some, you have some uncertainty, so it's minus 3 to 5 of logarithm 10, and minus something else that comes from unknown dynamics of reheating. So altogether you get something like 60 to 55, maybe to 50, depending on these dynamics. Okay, that's the origin of 6T foldings people are talking about when they discuss the inflationary scenario. So our interesting scales, cosmological scales, enter the exit the horizon at 60, maybe 50 E foldings before the end of inflation. Okay, so that has to be bear in mind. And there is quite a bit of uncertainty, since we really don't quite know what happens at reheating in particular. Well, it's model dependent, but if given a model, I will talk about models very soon. Given a model, you just can calculate what it is. And it's typical that I made quite a substantial error, range of the Hubble parameters. In the single field inflation, it's roughly of order of maybe 10 to minus 6, 10 to the minus 7, 10 to the minus 9, depending on your model. So it's model dependent thing. Yeah, that's because all what I don't know here enters logarithmically. Therefore, even though I can have Hubble parameter at inflation varying by several orders of magnitude, depending on the model, still logarithm of this is not particularly large number. Therefore, this 60 to 50 foldings, this span of 10 E foldings, more or less covers my ignorance of what precisely the inflationary model is, how reheating occurs, etc. So this E to the 10 is a large number, large uncertainty. It's not a theorem. You can design models where Hubble parameter is a lot smaller, and also you can design models in which your reheating lasts very, very long, and therefore you can have, instead of 50, you may have something like 40. But that's kind of unusual situation. Okay, that's one thing to remember. Another is that the single field inflation deals with one field. It's by definition it's single field. One scalar field. That's nothing simpler. So you think that the only relevant degree of freedom is a scalar field, minimally coupled to gravity, so that its equation of motion is homogeneous. So that's its equation of motion minus v prime, where prime denotes the derivative with respect to the field, v is the scalar potential, and another equation is that h squared is 8 pi. This is our Hubble Friedmann equation, 3 1 over m Planck squared, where m Planck squared is 1 over g, and the energy density for homogeneous field, phi dot squared plus v. Okay, that's field equations for homogeneous scalar field, which completely dominates the expansion of the universe. And the story, it's interesting that it wasn't immediate that people understood that this system is quite simple. The inflationary scenario began not quite from this idea of slow roll, although it was implicit, in fact, or even explicit in Starobinsky's paper on inflation. But now it's, I mean, the idea is straightforward. This is equation of motion for a particle in potential V in the presence of friction term with a friction coefficient h, and what you want to arrange is that the evolution is very slow. So you sit on the slope of the potential long time and very, very slowly roll down the potential. Okay, that's nothing simpler. Then in this regime, in the slow roll, you get very simple set of equations, which I write down here, and I have also on transparency. This is phi dot. Phi dot equals to minus v prime, and h squared is 8 pi over 3 times 1 over m Planck squared times v. So I'm assuming that, you know, if you have strong friction, then this term with friction dominates over the acceleration term, right? Your drop of honey slowly moves along your cup. And here, so the assumptions here is that phi double dot is much less than 3h phi dot, I mean modulus always, and also that 1/2 of phi dot squared is much less than v, so that the motion is slow, and then the Hubble parameter changes slowly in time, and therefore it's nearly constant in time, in other words, and so you're done. You're at inflationary regime. The Hubble parameter varies in time very slowly. Okay, so once you have these conditions satisfied, then you're automatically in inflationary regime. And I invite you to play numerical games. It's actually very easy. Even if you have inhomogeneous scalar field, if you just take arbitrary initial condition with large enough, well, I'm talking about the potential, for example, as a power law, which is not necessarily the case, but suppose you have power law potential phi, v of phi, and if you are sitting somewhere here, I will in a second tell more detail where, but if you are sitting far away, your field values are able to fluctuate a lot in the modulus. Even if you start off with more or less arbitrary initial condition, it is straightforward to do, you know, to do simple numerical calculations and figure out that whatever initial condition you throw, typically somewhere you're going to have initial conditions suitable for inflation. I invite you to do this simple, you know, game, and it does work. I mean. So anyhow, the idea is that whatever initial conditions are, if your field is high up in the potential, then once you do not have very strong inhomogeneities in the field, then you end up in the inflation regime necessarily, automatically. Okay, so when do these, what is the requirement for these conditions to be satisfied? Well, straightforward. You use these two equations to let me just flash them out here. You use these two equations and figure out that this 1/2 of phi dot squared over v, okay, You know what is phi dot here, you know what h here, so you just take the ratio of things which are known, you get that it's equal to epsilon over 3. You don't need to use anything but these equations here, right? You know what is phi dot, you know what is h in here, so you calculate this ratio, and this epsilon is famous slow roll parameter, which is v prime squared m Planck squared over 16 pi v squared. Okay, that's what's written up there. And then you, of course, can calculate also h dot over h squared, which tells you how much the Hubble parameter changes in Hubble time, right? For that, you differentiate this thing in time and use the first slow roll equation, and you find out that it's equal to epsilon. So this parameter governs how fast the Hubble parameter changes in time in the Hubble in one Hubble time. Okay, so if this parameter is small, then the Hubble parameter indeed varies slowly. That's another face of this epsilon. Now the second, the first of these slow roll conditions reads as follows: phi dot dot over 3h phi dot. You have to calculate the derivative of phi dot here, and time derivative of phi dot involves second derivative of potential. So this guy is equal to 1/3 of eta, where eta is another slow roll parameter, which should independently be small, and this is v prime prime m Planck squared over 8 pi v. So you require that both epsilon and eta are small, and then you're in inflation regime. Okay. It's not an innocent, of course, to take these parameters to be small, because for power law potentials, as you know, or as you can figure out from here, for power law potentials, if my epsilon is here, okay. If my potential is power law, then this ratio, for example, is inverse of phi. So for potentials v of phi to the nth, this guy will be n squared m Planck squared over phi squared, whatever 16 pi phi squared, which means that epsilon is small, provided that the field is super Planckian, that the field value is greater than the Planck value, which is kind of a little bit troublesome. But remember that this phi is not energy density or anything similar to energy density, and therefore, therefore, even for super Planckian phi, you can still think of classical description of general relativity. It's another story that you may suspect that there are terms in the potential that are of order of phi to the nth to m Planck to the n minus 4 with arbitrarily higher n, but you have to assume that for some reason these guys are absent. Okay. Or coefficient of them are small. So similar requirement for inflation comes also from considering eta. If you have power law potential, then of course it's going to be again n minus 1 m Planck squared over 8 pi phi squared, which is again the same story. Okay. Right, now what turns out to be important, let me give you the result of this simple calculation. What turns out to be important is the values of these parameters at eta and epsilon at the time when our universe, our visible universe, exits the horizon at inflation. At the time when interesting perturbations, in other words, of cosmological scale, exit the horizon, right? Turns out that these determine the properties of perturbations in the universe. To this end, one calculates a number of e-foldings. Okay, so you know what it is. It's before, which is A at crossing and A today. And then A end. On the one hand, we know that this is something like 60 or 50. On the other hand, we know that it's equal to integral of h dt from t crossing to the end of inflation. And then you can redo this as an integral over phi by using these two slow roll equations. Okay. Since phi dt is d phi over phi dot, you know what phi dot is from here, you know what h is from there, and you end up with the relation that it's equal to integral from phi end to phi crossing, phi end to phi crossing of 8 pi v over m Planck squared v prime d phi. Okay? So once you know the left-hand side is 50 or 60, then you know what and you have your potential, your favorite potential at your hands. Then you know what is the value of the scalar field at horizon crossing. And so once you know this field at horizon crossing, you can calculate epsilon and eta at horizon crossing. Okay. And for example, again, for power law potentials, epsilon and eta are n over 4 ne, and eta is at the horizon crossing is n minus 1 over 2 ne. Okay. Those who didn't do this calculation, it's pretty simple, right? You do this integral for power law potential, which is essentially phi d phi, phi squared, right? Modulo this factor of n in the denominator. You relate, therefore, number of e-foldings to the phi crossing. It's quadratic on the right-hand side in phi crossing. And then get in here, you express phi crossing in terms of the number of e-foldings. You plug it in here and in there, in here and in there, and you find these expressions. Okay? Simple calculation. Okay, so that's the inflation in a nutshell, the inflation scenario itself. But as I told you, the main virtue of this scenario is that it's capable of generating perturbations in the universe. So the rest of my lecture is going to be devoted to the perturbations in the inflationary scenario, how you generate perturbations. Okay. Well, let me first discuss perturbations of a massless scalar field, or equivalently, tensor perturbations. We know that, just a spectator massless scalar field, not inflaton itself, not this guy phi, but rather spectator scalar field, or tensors. We know that tensor perturbations obey the same equation as the massless scalar field in the background of expanding universe. So let me write down equation for massless scalar field, or the same thing, tensor, in terms of conformal time. So this is the equation plus k squared phi. We used this equation already when we discussed gravitational waves, remember. Prime denotes the derivative with respect to eta, and we know that for exponentially expanding universe, a of eta is -1 or h eta. Okay. Of course, at inflation, the universe doesn't expand exactly exponentially, but it expands almost exponentially at a given epoch. And I will be interested in epoch when the perturbation crosses the horizon in, when the crosses the horizon out. Sorry, when at epoch when the perturbation phi starts becoming superhorizon. Because we know how these solutions to this equation behave at early times when they are subhorizon, well, within the horizon, then this is WKB solution. And we know what survives outside the horizon. It's a constant mode, right? So we just have to match these behaviors near the horizon crossing. Okay? So, and for this matching, we can safely neglect to the zeroth approximation in the epsilon data in slow roll. We can neglect the fact that h itself depends slowly on time. But let me come to this equation, and let me define phi equals chi over a, where chi is a new field. And this is dictated by the fact that I want to cancel out the second term in the equation to get the equation of Schrödinger type. Or in other words, remember we have action for this massless scalar field and modular overall factor gravitons. This is it, this d3x eta mu nu d mu phi d nu phi, right? So this change of variables is such that this term here goes away. And we have kind of canonical kinetic term, 1/2, canonical kinetic term for high field, right? So in terms of high field, if you do the integration by parts, you get integral d eta 1/2 d3x d eta chi squared minus gradient, special gradient of chi squared plus a prime prime over a chi squared. So in terms of this chi, the only effect that expanding universe has is this third term. Okay, and accordingly, the equation for chi has this simple form: chi double prime minus a prime prime over a chi plus k squared chi is 0. Okay? And again, this a prime prime over a is proportional to the Hubble parameter squared, or, well, okay. Anyway, when this term is large, when this term dominates, you are in the superhorizon regime. When this term dominates, you are in subhorizon regime. And remember, in our particular case, a prime prime over a equals to 2 over 8 squared. Okay? So we are in subhorizon regime when k eta is much greater than 1 modulus, and superhorizon when k eta is much less than 1. And remember, eta starts from minus infinity formally, or early times are minus, correspond to negative large eta. So we are subhorizon at early times and superhorizon at late times. Okay? As promised. Now the solution, so what we want to do, we want to say, okay, I have a quantum field, right? My fields are quantum. I have a quantum field. I know that early in the inflationary epoch, it oscillates just like the conventional field in Minkowski space. So I impose an assumption. I assume that I'm in vacuum originally, right? And if you don't, if you are not in vacuum corresponding to the quantum of these fields, if you don't have anything particularly, strange, then all your particles will be diluted away by inflation. So it's kind of natural assumption which goes into this calculation. So we are in vacuum with respect to at early times, when this term is negligible, natural assumption is that we are in vacuum. This is called Bunch-Davis vacuum. And in principle, in the expanding universe, you can have all kinds of vacua. You can have different definitions of vacua, and this particular definition is called Bunch-Davis vacuum. So we assume Bunch-Davis. So if we make this assumption, then once this term starts to be important, we have the quantum field theory, free quantum field theory, but in an external field. And we know that quantum field theory in an external background, which changes in time, there will be particle creation, right? So you can think of generation of perturbations in this field, in this case, as particle creation, an analog of particle creation by external fields. This language is not particularly useful because we are interested in what happens to this field after horizon crossing, right? So if my field has wavelengths longer than the horizon, then it doesn't make sense to talk about particles. So particle creation is not very appropriate here. But you can think of this process as analog of particle creation. And in fact, it is. If you follow this field towards our present epoch, and if it becomes subhorizon again, and the perturbations of this field oscillate, they can equivalently be described as collections of particles, and therefore it is particle creation. But you see these particles as particles only after the wavelength becomes shorter than the Hubble size, right? Otherwise, they're just huge fluctuations of your field. Okay, anyhow, what we that's the language I'm going to use. I'm going to use the language of a field rather than particles. But in any case, initial condition is this, right? Your chi initially, as eta goes to minus infinity formally, and physically in the subhorizon regime, should go to free massless scalar field, right? That's the way you have quantum fields. And what it is, it's just a standard expression for quantized scalar field. Okay. Once you drop out this term here, it's just a Lagrangian or action for a free scalar field in Minkowski space. So you immediately write down that it's equal to minus ik eta, that's the time-dependent part, plus ikx, space-dependent part. Normalization, which is conveniently chosen in this fashion, to k 2 pi 3 over half, and a of k, plus Hermitian conjugate. Okay, that's my expression for the field. It's not what is usually done in courses in particle physics and quantum field theory aimed at particle physics. Normally there is a relativistic normalization. Here I use normalization, which is convenient because with this normalization the commutational relation between creation and annihilation operator, which are here, is just a delta function without any coefficient. Okay? That's useful for doing calculation in your head without using paper. But that's, of course, a matter of convenience. All right, so that's the usual expression for quantum field in Minkowski space. And my field chi should tend to this free field in Minkowski space. But of course, I'm considering now this equation as a Heisenberg equation for this field, right? Of course, this field will no longer have the same form once you are in superhorizon regime. It will be a constant. It will not be oscillating. It will be a constant. Okay? So you have to make matching. You have to match this field to a constant. Okay? To time-independent field. Okay? You should match it at the moment of time when all right, let me just do matching precisely. It's straightforward. Now I want to solve this equation near the horizon crossing. Near the horizon crossing, my scale factor is nearly this, with understanding that h is the Hubble parameter at horizon crossing. So this is 2 over eta squared, right? So it's a Bessel equation again, right? So this solution that tends to the exponential behavior chi minus equals e to the minus I k eta. That's what's here, but that's no longer true in the superhorizon regime. The solution is actually this 1 minus over k eta, and that's the Hankel function of 3/2 index. Okay, so that's the solution to this Bessel equation here, which indeed oscillates like e to the minus I k eta at large eta. But once you're in superhorizon regime, then this term dominates. So this solution in the superhorizon regime, chi as eta, k eta is much less than 1 modulus, is obtained from here by just substituting the exponent by this power law, I over k eta, right? So you immediately get that chi is integral d3k 1 over square root of k 2 pi 3 half. That's my coefficient. And then instead of e to the minus ik eta, I insert minus I over k eta. So I get 1 over k eta minus I a k plus Hermitian conjugate. Okay? That's the behavior of my chi, and phi, the original field, is related to chi in this manner, and I recall again this relation here, that A is 1 over h times eta. So phi in the superhorizon regime will be this. That's the final formula for the quantum field in the superhorizon regime. Again, the same factor here. And instead of this, when I divide by 1 over h eta, what I'm doing, I have to divide, yes, by 1 over h eta, then this eta will cancel out, and I will have h over k, and then I a k plus minus I a dagger k. Okay? So this is a static field as promised. It's independent of time, right? And what's most important here is that it contains k to 3 half in the denominator. And the claim is that if h is a constant, is independent of k, then this is the field with flat spectrum, flat power spectrum. So you see, this field is a linear combination of creation and annihilation operators. Its vacuum expectation value of its correlators obeys Wick theorem, right? It's a free field, after all. It obeys Wick theorem, so it can be viewed as the Gaussian random field. Okay? So instead of considering this field as quantum field, you can think of it as Gaussian random field, because once you start calculating the correlation functions, you are going to get, correlation functions that obey Wick theorem. And that's the same thing as Gaussian random field. Okay? So I'm dealing with Gaussian random field, and its power spectrum is inferred from, remember our definition of power spectrum. We said that let's calculate phi squared of x expectation value and define power spectrum such that it's given by this expression here, right? That's our definition of power spectrum. So let's calculate the left-hand side. It's straightforward to calculate the left-hand side because this thing here, this product here, twice averaged in vacuum gives you just one delta function of k and k prime. So it's essentially 1. So immediately I write that it's equal to integral d3k 1 over 2k 2 pi cube, right, since I have two of these fields, h squared over k squared. And that's it. Okay? So if you do the integrate over angles in momentum space, then I cast this in precisely this form, dk over k, right? And here is k cubed here, d3k. So indeed I have dk over k, and the rest is h squared over 2 pi squared. Okay? So if h is independent of k, then this is flat power spectrum. In general, p phi equals h squared over 2 pi squared. That's the final formula for a scalar field. Okay? In fact, there is some dependence on momentum because my modes exit the horizon at different times, and at different times this h is different, right? So if you exit the horizon later, which is true for short modes, then this h is smaller. The Hubble parameter decreases as the field rolls down, and as the inflaton rolls down. So the Hubble parameter decreases in time, and therefore phi should be slightly red, right? The shorter wavelength exits the horizon later on when h is smaller, and therefore shorter wavelength has less power, a little bit. But this is actually the final result for gravitational waves, except that this action I wrote, and I quantize this field as canonically normalized field, right? But in fact, if I want to calculate the amplitudes or power spectrum of metric perturbations in gravitational waves, then I have to take into account that my metric perturbations are not canonically normalized. Remember, we had the action for metric perturbations as m Planck squared over 64 pi. Remember, that was my claim in one of the lectures, that the action for the metric perturbations is this, therefore x dh alpha squared and sum over alpha, where alpha is the polarization index. There are two polarizations of this alpha, right? So the canonically normalized field phi alpha is actually m Planck over square root of 32 pi times h alpha, okay, from here. So for each of the phi alpha of a given polarization, I have this power spectrum, and from that you get the power spectrum for h alpha, and power spectrum for h alpha for each of the polarization is 8 over pi h square over m Planck square. Okay, so the total power spectrum for tensor perturbations is 16 over, you sum up over all of the two polarizations, that's final answer, h squared over m Planck squared. Okay, and this guy h depends on k because different modes exit the horizon at different times. Okay, that's the final answer for tensor modes. This is valid for master scalar field. This takes into account that canonically normalized scalar field is related to metric perturbations in this fashion. Okay, so this, by the way, tells you that the fact that this tensor power spectrum or tensor power is not very large, it's at most on the order of 10 to the minus 10, roughly, tells you that the Hubble parameter is at most on the order of 10 to the minus 5 in terms of the Planck mass. And that's nice. That's nice because that tells you that we are not dealing with Planck scale physics. If inflation is correct hypothesis, then it occurred at at the Hubble scales very much below the Planck scale by at least 5 orders of magnitude, which is reassuring. This is known since, all this is known for a long time. Okay. Fine. This is all for gravity waves. And of course, gravity waves don't care about the way the inflation happens. They only care about geometry. They only care about the expansion rate of the universe. They don't care who is doing inflation, what is the inflaton, what are its properties. Everything you need to know is the Hubble parameter at the time when the mode exits the horizon. That's very nice and intuitively clear picture that gravitational waves get created by the very fact that the universe expands fast. Okay. For the inflatons, the situation is different. These are gravity waves, vector perturbations. But what we want to know also is scalar perturbations. Okay. Scalar perturbations come from the only source of energy density, which is inflaton. Right? For density perturbation, situation is not as simple. Well, first of all, let me notice that the density perturbations, the inflaton field itself, doesn't, or perturbations on it. So I'm going to write down that the phi, the inflaton field itself of x and time, eta, is the phi c. I change the notation. Phi c will be my rolling classical homogeneous field and perturbations. Okay, how do I write them? Phi perturbations of the inflaton field. And the equation for perturbations of the inflaton are not this one, is not this one, because you have also the scalar potential, right? So if you do all your, you have here right, you have here also term due to the potential, and remember that the potential enters with extra, so my action in terms of eta has a to the fourth as the square root of g. Now eta mu nu 1 over a squared, sorry, yeah, mu nu d mu phi d mu phi d nu phi, right? With a squared coming from the inverse metric. And then I have minus v. So v has extra factor of a squared. So my equation for the inflaton will be, let's see, plus a squared v prime. Now for perturbation, it's going to be v prime prime times phi equals 0. Okay? Right. That's my equation for the perturbations of the inflaton. If I again introduce chi equal to phi over a, phi times, if I write down that phi is chi over a, then my equation will be chi prime, our old one, minus a prime prime over a chi prime plus k squared plus v chi plus v prime prime a squared chi equals 0. Now it's confusing. This is the derivative with respect to phi. Let me write it down here. So this prime and this prime are different primes. Okay, this prime everywhere except here is the derivative with respect to conformal time. Here, this is derivative with respect to phi. So anyhow, I will immediately erase this because I can compare this term and this term here. Okay, this term here. So let me compare this term and this term. This so I compare a prime prime over a cube versus the second derivative of the potential with respect to phi. Okay, and this guy you can easily convince yourself it's equal to 2h squared for the since my a is minus 1 h eta, plug this in here, get 2h squared, and this is second derivative of v. So the ratio between these two is just equal to 3 over 2 eta. The other way around. Let's see. Yeah, v phi phi equals 3 over 2 eta minus 1, where eta is the slow roll parameter. Okay? So this term here is dominant as compared to this term by the slow roll parameter. Okay, so if you work to the leading order in slow roll, you can forget about the inflaton potential once you are calculating the perturbations of the inflaton. If you want to go better, if you want to calculate, for example, corrections due to the first order or second order corrections in slow roll parameters, then of course you have to remember that there is this term here as well. Okay, but to the leading order in slow roll, you can forget about this term, and we come back for to the equation for the scalar field. Okay, for the perturbation of the. But that's not the whole story, because this would be true if my inflaton was spectator, but it isn't. The perturbations in the inflaton field induce also perturbation in metric, scalar perturbations in metric, and therefore this is actually not the correct equation here. You have also contributions coming from perturbations of metric, which by themselves are linearly related to the inflaton. Well, is it tractable? The answer is yes, it is. And I'm not going to go into much detail here, but let me give you the idea and the way one can calculate and get to the answer soon. Remember, we don't want to calculate the perturbations in the inflaton field per se, or metric perturbations, the gravitational potentials themselves. What we are actually interested in is the quantity that remains constant in time all the way from inflation to radiation domination. Remember, we introduced this quantity zeta, right? Which is the invariant characteristic of the density perturbations and associated gravitational potentials, right? And we had it that zeta we had one expression for it, which was psi gravitational potential plus A prime over A times V, where V is the velocity of the medium. Now, we have to understand, so we would like to have an equation for this zeta, and we know that once you are in the superhorizon regime, this guy doesn't change in time. It remains constant. So we would like to have an equation for this zeta. We would like to find what this zeta is in the superhorizon regime, and then we immediately know what is the initial condition, what is the primordial density perturbations in the later stages, right? That's the idea. Now, the question is, what is the velocity, right? Since we are in the inflationary stage, there is no fluid at all. What is this V? Well, let's use the definition. The definition is that delta Ti naught, by definition, is minus P plus rho. These are background pressure and energy density times V I. That's the definition of velocity. We can view this as a definition of velocity, right? In other words, if there is such a V that delta T has this form, then we are in business. Then we are in the ideal fluid approximation, and Vi serves as the velocity. Okay? Good. So we now recall that T mu nu for our inflaton field equals G mu lambda d lambda phi d nu phi minus delta mu nu times the Lagrangian, half of G lambda rho d lambda phi d rho. This is for inflaton, d rho phi minus V. Okay, that's our definition. That's the result for the energy momentum tensor. So what I would like to do now is to insert here phi as phi c plus phi curl, which is the perturbation, and figure out what this mixed energy momentum tensor is. Easy. Delta T I 0. Okay, so mu is I 0, sorry, mu is 0, nu is I. Let's see, where is it? It's 1 over A squared which comes from the metric here, times, and here I have 0 for lambda and I for nu. And I want to do this calculation to the leading order in perturbations. So I have phi c prime times di phi. Okay? Where prime denotes the derivative of the spectrum metric. Okay? Very good. And then, what is P plus rho? I should calculate as well the 0, 0 and special components of this energy momentum tensor, but only to the leading order. And to the leading order, I obviously get that rho is modulo 1 over a squared, Yeah, okay. Sorry, let's see. Well, anyway, P plus rho is phi prime squared over A prime, over A squared. Okay? Phi classical. At the classical level. Remember, the energy density rho is a half of, let me do this in the cosmic time, T, and pressure is the opposite, half of phi dot minus V. Okay? This is the expression for the energy density and pressure for arbitrary scalar field minimally coupled to gravity. So the sum is phi dot squared. In terms of phi prime, it's phi prime squared over A squared. Okay? So why did I need that? I need that to insert in here and figure out what the velocity is. So velocity Vi is simply minus di phi over classical V prime. Okay? So I'm in business. My system looks like a perfect fluid. If I identify velocity with the derivative of phi, of the perturbation of the scalar field, divided by phi prime square, with the classical field prime. Okay? So my potential V is minus phi over phi C prime. And that tells you what your variable zeta is. Okay? Remember, since we are in perfect fluid approximation, psi and phi are the same thing. Psi is equal to minus phi. Phi is another Newtonian potential. That answer is not component of metric. So in the end, I have my zeta equal to minus phi plus A prime over A, which comes from here, phi C prime, which comes from the expression for velocity I erased, times phi. That's how the perturbation zeta, which characterizes for me the density perturbations in the superhorizon regime, that's how it is related to this field phi. Okay? And gravitational potential phi capital. So basically, you immediately figure out that the coefficient between the two determines how perturbations in the field phi are related to the perturbations of invariant zeta, of the invariant quantity zeta. So basically, already from here, you can guess that zeta in superhorizon regime will be equal to, with minus sign, A prime over A times phi C prime phi, where phi is this guy with nearly constant power spectrum, and this has to be evaluated at the horizon crossing. That's a guess, right, for the time being. But in fact, this guess is correct. This guess is correct because, let me give you, let me write down the equation for you, which you can obtain by using our nice equations for density perturbations and the potentials. You can cast, by manipulating with these equations, you can get the following equation for zeta itself. So all the system of equations we had for Newtonian potential and the field that you can write down as we did for density perturbations, they all reduce to one and the same equation of this form, which is actually quite simple. And z prime, zeta prime plus k squared, zeta equals 0. That I'm not deriving, but you can derive this equation, where z is this combination, a squared times phi c prime over a prime. So by manipulating the equations that we have written before, with identification that zeta is this, the velocity we determined that v is minus phi over phi prime c, and energy density and pressure calculated by using the expressions for energy momentum tensor in the of the scalar field, of the inflaton field. Reshuffling these equations, writing them in terms of this variable zeta, you obtain this equation here. Okay. And by the way, this equation is very nice because it holds no matter are you in the slow roll regime, in fast roll regime. Once you are dominated by a scalar field, phi, once you're, and there is nothing else, then the perturbation of the scalar field, together with induced gravitational potentials, they always obey this equation here. Okay? Good. Now, in our case, in the case of slow roll, you understand that A prime, let's see how it goes. Right. You understand that this expression here can be written as A times A squared over A prime, phi prime over A, and this is A times phi dot divided by H, right? H is A dot over A, which is A prime over A squared. Now, this guy, phi dot over H, varies slowly in time. That's our slow roll. So, Z modulo a slowly varying factor is equal to A. So we are back to the equation we had before, right? We're back to the equation we had for massless scalar field in the background A, right? If we say that Z is the same thing as A, modulo constant, then we are back to the equation we were solving when getting at this expression here, okay? So, in the slow roll approximation to the zeroth order in the slow roll parameters, you're back to the equation for the scalar field for minimally coupled scalar field. But now this zeta is to be understood as, sorry, this must be prime here. This zeta must be understood as this combination here. Okay. Now, early in the epoch when the perturbations were sub-horizon, this phi potential is small. You can show that. It's suppressed by 1 over k squared. So basically, the fields zeta and phi are related by the factor a prime over a over phi c prime, which is h over phi dot times zeta, okay, times phi. Okay, so there is the overall normalization factor h over phi dot, and as promised, this relationship is here. At early times, phi is canonically normalized scalar field. At late times, this zeta freezes out. So basically, you can take this h over a dot out of the whole story, of the whole expression. So my zeta finally is indeed equal to, with minus sign here, but sign doesn't matter. It's h dot, h over phi dot, c phi dot classical times phi, where phi is the power spectrum which I erased, h squared over 2 pi squared, and this is an enhancement factor for this zeta. Okay. So I immediately get the scalar spectrum. The scalar power spectrum equals h over phi dot c squared at the horizon crossing, as usual, times h squared over 2 pi squared at the horizon crossing for the given mode. That's the standard result of inflationary theory, that you get this power spectrum for scalars and this power spectrum for tensors. Okay, and then the point is that both power spectra, one of them depends only on the Hubble parameter, whereas this one knows about the evolution of the inflaton. Not only Hubble parameter, but also inflaton evolution counts here. Okay, and then you immediately can rewrite this zeta. Rewrite this by using the slow roll equations in the form which is this: 128 pi over 3 times v cube over m Planck to the 6th and v prime squared. Okay. So if my potential is a power law, g times phi n, this is obviously proportional to g, to the coupling constant. Or if it's n is 2, then it's a mass squared, right? So by choosing appropriately this coupling constant, you can fit the amplitude of scalar perturbations, right? The trouble is that you need very small coupling constant in Planck units, right? Since my zeta here is very small, right, then p zeta is 10 to the minus 9. This translates into the smallness of the coupling constant, right? So in Planck units, this coupling constant should be small. Small meaning if you are in lambda phi to the 4th theory, say lambda phi to the 4th, if this, for this potential, this lambda should be a order of 10 to the minus 12, which is characteristic of the whole set of inflationary theories. You need very flat potentials, very weak dependence of potential on the field at super Planckian fields. which I consider pretty problematic. You need, I mean, if you are thinking of conventional phi squared or phi to the fourth theory, then there is no reason whatsoever that the coupling constants are very, very small, or mass must be very, very small here. There is no, you know, obvious reason why this should be the case. And yet you need very small couplings to fit the small amplitudes of primordial density perturbations. So to me it's rather problematic. But if you agree to live with that, you also can calculate tilts, the dependence of this P on K. How do I calculate that? Well, I know that the A crossing is e to the minus n e, and it depends on k, right? So this is the number of e-folding before the end of inflation. So it's proportional to. Okay? On the other hand, I would like to have k over A crossing equal to the inflationary Hubble. Okay? So I have NE of k proportional to the minus logarithm k, right? Am I right? Yeah. Which means that dne over d phi crossing times d phi crossing over d logarithm k equals minus 1. Okay? So n is this plus constant. So this tells me how the value of the field at which the horizon is crossed depends on momentum k. Okay? And of course, everywhere here you have dependence on the crossing phi, because this is just a function of phi which is taken at the value of phi when the modes cross the horizon out, right? And this tells me how this crossing phi depends on the logarithm. Now, NE we wrote as a function of phi. I erased this, but we had the expression that okay, anyhow, from that we find that d phi crossing over d logarithm k is just equal to minus m Planck squared. That was the integrand v prime over 8 pi v. Inverse of integrand for the expression for the number of e-foldings. Okay? So with this, we immediately calculate the tilt in the scalar spectrum, for example. Okay? Since what I want to calculate is d logarithm p zeta over d logarithm k, and this is nothing but ns minus 1. Remember, we parameterized p as power law of k to ns minus 1. So you immediately figure out that this is equal to 3 v prime over v minus 2 v prime prime over v prime times d logarithm phi crossing, d phi crossing divided by d logarithm k. Okay? This we calculated, it's here. So you plug in that expression. You recall our expressions for eta and epsilon, and you get minus 6 epsilon minus 2 eta. You do get non-trivial tilt, which depends on epsilon and eta, which themselves depend on the shape of the potential. Okay? And similarly, what you get is a nice result that the tensor nt is minus 2 epsilon. And finally, the ratio of the two, which we called R, P tensor over P scalar, is actually equal to 16 epsilon, if I remember correctly. Yeah, 16 epsilon. So for your given favorite model, you calculate epsilon at 60 foldings before the end of inflation. You calculate eta. We did that for for power law potentials. You plug in here, you get tensor to scalar ratio. You plug in here, you get the scalar spectral index. And what's nice is that there is a model independent relation between R and tensor spectrum. That would be great. That would be fantastic if we would be able not only to see the effect of gravity waves on cosmic microwave background, but also get some idea of what the tilt in the power spectrum of gravitational waves is. And then for single field inflation, the slow roll regime, you have this relation. If you check it, that would be triumph. I'm not sure I will live to this to this point. Maybe some of you will. That would be triumph of simple single field inflation theory. But anyway, single field inflation theory, once you choose your favorite potential, predicts for you everything. All tilts, all the amplitude you don't predict, you need to dial your coupling constants, but all the rest you predict once you have a shape of your potential. Okay. Are there problems? Yes, there are several problems with all that. One is that you often have to go beyond Planck scale in terms of field, but who told us that the canonical normalized field is the right notion, and it's only with canonical normalization that you have to go to the super Planckian value of the field. And in any case, why not? Second, you need, that's more serious to me, is that you need to dial, you need to tune the parameters in order that you get the right amplitude of scalar spectrum. That's not as pleasant, but nothing wrong with that. Otherwise, you're in good shape. And the worst thing is that gravity waves haven't been seen, and therefore many of the potentials, say quadratic power law is nearly excluded, quartic is excluded, is ruled out. So you have to be thinking in terms of more exotic from our everyday life inflaton potentials, but I mean, our everyday life may have nothing to do with what happened at inflation. So that's my inflationary theory in one lecture. Hope tomorrow it will be less trivial. Okay.
Is that correct that this model, in absence of other fields, is dual by Weyl transformation to the modified gravity law?
I'm not, yeah, at least locally. I'm not sure if there is a global statement that you can make a Weyl transformation to f of r theory so that for any value of the field phi you have one-to-one correspondence. That I'm not quite sure about. But locally it is true, yeah.
Well, as far as I
Locally means in some part of the field values, not in the entire space of field values, but in some part of space of field values, it is equivalent, yes.
But one of the Starobinsky's models is called f of r.
Yes, the original Starobinsky model is equivalent to this. The original Starobinsky model has to do with r plus r squared, this kind of model, and indeed by doing Weyl transformation you can translate it into scalar field with potential which actually is quite different from power law. It's like this. It's V. This is phi.
Yeah, there is a quite exotic expression.
No, it's just here it's basically 1 plus e to the minus phi over some constant. That's roughly it.
So will this kind of thing work? And I do not understand how it works when there are other fields that break this duality.
Well, you can have extra field. So,
I mean standard model fields.
huh?
I mean standard model fields.
Yeah, you can. Well, you can redefine the metric. You have make while transformation of your metric, there will be interactions between the inflaton field and standard model fields. There is nothing wrong with that. You need interactions of the inflaton with standard model fields, otherwise you will not be able to reheat the universe. So it works. There will be interaction between the inflaton and the standard model fields, definitely. But that's what you need. That's what you want to have. In Starobinsky's language, this r plus r squared theory had massless gravitons and also massive particles, which in this language correspond to excitations in here. And he needed these guys to be unstable, to decay into standard model particles. And that's precisely what we are talking about, right? We want them to interact with standard model particles.
How can we
In
discriminate?
this language, they interact as as the components of metric. In the Weyl rescaled language, it's just inflaton that interacts with them, with standard model particles.
But if I understand correctly, if we have standard model fields, then we cannot transform from modified gravity law to the scalar inflation.
Oh, we
right?
can.
Always?
Again, locally in field space. But modulo this qualification, yes, we can either use what's called Einstein frame, or we can use Jordan frame. In other words, we can reshuffle from f of r theory to scalar theory with Einstein term, but with specific some interactions with the standard model meta. It all transforms into interactions with the standard model meta.
Okay, thank you.
Other questions?
Well, we did everything in d equals 4 dimensions. There is some generic predictions by putting d dimensions and
Generic.
or
no, I
everything
don't know
is-
of any generic prediction.
everything is model dependent.
Everything is model dependent because you have to stabilize your sizes of these extra dimensions. Now, depending on how you stabilize and at what scale you stabilize them, you have different picture. For example, if you stabilize the extra dimension at scales larger than the Hubble parameter at inflation. And basically they stay frozen, right, during inflation, during the four-dimensional picture back. If you stabilize them at lower scales, then they start to, feel that inflaton, that there is inflation around. They start to evolve themselves. And then again, it all depends on how they evolve and what, so I don't know of any, do you know of any generic prediction? Okay. None of us three knows any generic prediction.